time you can attend it online. Okay, otherwise you can get the recording. That last session was on YouTube also, so you can get the video from there only. Okay, so we have done this question now. Okay, let me have. All right, so my pen is calibrated and now we can start further. So this question we have done. So we are talking about the binary number and binary coding. Okay, so if you can see that binary number, that is representing the information that has k number of bits. Okay, and that k bit can vary for the next number. Okay, like if I give you an example here, let's say 7 can be represented in 4 bit as 0111, isn't it? Okay, now if we want to represent 8, okay, this is 7, and what about 8? That is going to be 1000. Okay, since it is 4-bit number only and all 4 bits are flipped. Okay, can you check here? This is also flipped from LSB to MSB. Entire bit is flipped. Okay, so more than one bit changes every time. Okay, so if we simply represent a binary number system for any particular information, it is possible that number of bit flips are more in even consecutive numbers. 7 and 8 are adjacent numbers. Okay, and the number of bit flips are more. Okay, so in that particular case, it is not possible to identify whether information is wrong or not. Okay, whether your information that you have received through certain transmitter is correct or it is incorrect. Okay, lots of mediums are there that could actually harm your data. Okay, maybe mechanical noise, maybe electrical fluctuation, maybe transmission wear and tear. Okay, due to any particular maybe high voltage. Okay, so there are lots of sources that could harm your data, and harming means it can change the value, it can flip the particular bit, any bit. Okay, and that will give you the wrong information. Okay, so there should be certain mechanism through which we can represent our data in a coded information so that we can easily identify whether my code is correct or not. Okay, so lots of uh, mechanisms are there that through which we can actually represent our binary information into the coded one. Okay, so we have already seen yesterday that BCD is one of them. Okay, XS3 code is also there. 84 minus 2 minus 1 is there. 2421 is also there. Okay, rather than 8421, 2421 is also there. Okay, and gray code is also there. All right, so I'll come to that one by one. Okay, this we have already discussed about now. Like we have information like we have colors, red, green, blue, and all. Okay, so all vibrant colors are there, and that could be represented in 3-bit binary because there are you can see that 7 number of colors are there. Okay, so these 7 numbers of color can be represented by minimum 3 bits. Can we represent it by 2 bits? Why not? So possible ranges are only 2 to the power 2, starting from 0 to 3. Okay, so 0, 1, 2, 3. So 4 information can be represented by 2 bit only. Okay, 8 informations can be represented by 3 bit. Okay, 16 information can be represented by 4 bit, and so on. Okay, so we should select as much as compact number of bits so that we can represent the entire information. Okay, so 2 is inefficient, 4 is also inefficient because we are wasting the memory. Okay, after 7 we are not going to utilize all remaining 8 to 15. Okay, so that is going to be waste. Okay, so 3 is very much compatible for this particular representation. So here you can see that 002 triple one is representing this information. Is there some value which is missing? 100. 1004 is missing. Okay, that is up to your choice. 4 miss करना है और last वाला ignore करना है. Either 000 is to be missed. Okay, that is your choice. How do we represent the information? Because one value is excess. Okay, that 8 possibilities are there. We need to represent the 7 one only, 7 informations. So one is additional. So whatever you like to ignore that. Okay, so code 100 is not used in this particular case. You can miss any particular one. Okay, why code 100 is removed? So before ignoring anyone, we must know that whatever data you are using, whatever representation you are using, we can easily decode. Okay, when we encode any particular information via a number system, binary number system, okay, then decoding must be also unique. Okay, let's say I'm having some representation over here. Okay, let's say this is the color information transmitted from one particular channel to the receiver. All right, so what color do you have received here? So from transmission and receiving, we have to combine the number of bits. Okay, so this is the first bit that is to be received. Okay, so first 3 bits are combined to get the information from this particular coding table. Okay, so this is going to be the red information. Okay, then next 3 bits, and that is going to be blue. Then next 3 bit, that is representing the violet, and this is indigo. Let's say we have received only this at the last. What about this? 10, 2-bit is not available to us. So it is possible that whether the last bit is missed during the transmission, or that is flipped, or that is lost. Okay, so we cannot uniquely decode this particular value because it could be 100, it could be 101, it could be, okay, because this particular place can be simply replaced by 0 or 1. Okay, so we cannot uniquely identify whether it is going to be 0 or 1. So what we can do to check this particular information, whether it should be 1 or 0? So we must have the error handling mechanism. Okay, so parity code, we can append a parity code along with this to check whether whatever information we have received is correct or not. If there is some missing information, then we can fill it out. Okay, so that code actually plays important role. The binary codes plays important role in identifying the information correctly. Okay, so number of bits required, that we have already discussed, that compact number of bits must be selected for representing the information. Okay, that we have already seen in the previous example by 8086 addressing mode. Okay, there we have seen that 20 address lines can represent how much? 0 to 2 to the power 20 number of addresses. All right, so this m will represent the number of elements. Okay, so you have 7 number of informations in the previous example, so m is going to represent the 7 here. Okay, so the value 2 to the power something may be equal to or greater than this. Okay, so that n could represent this particular information. So in this particular case, n is going to be 3. Okay, so 2 to the power 3 is 8, which is sufficient enough to represent all this information. Okay, All right, there is a question. How many bits are required to represent the decimal digits with binary code? Decimal digits are 0 to 9. Okay. So 10 informations are there. So at least 4 bits are required, na? Okay. Is that clear to everyone? Like this particular question says that we need to represent decimal digits, and decimal digits are 0 to 9. Okay. So these are 10 quantities that could be represented. Okay. So 10 quantities can be represented by how many number of bits? At least. So here we have seen that 7 number of informations can be represented by 3 bits. Okay. So these 3 bits are inefficient to represent this 10 information. Okay, because that is going to turn up 2 to the power 3 as 8. So only 8 information can be represented. So 2 to the power 4 is the sufficient value. Okay. So 4 bits are required to represent this much. Okay. So how many information is going to be wasted? Like useless code. If we represent decimal number system by 4 bit, how many code words will be useless? 1. Yes. So after 9, let's say, just look at the possibility. 4 bit can represent the hexadecimal, 0 to F. Okay. But your requirement is to represent 0 to 9 only. Okay. So A to F is going to be useless code. All right. So that 6 number of code words will be useless. Okay. Such kind of questions have been asked in GATE exam. Okay. So you have to be like, these are the very basic terms, and you can miss it. Okay. तो आप इसको थोड़ा सा फोकस रखिएगा. All right. So number of elements representation, there are n digits and the radix is r. So there are r to the power n distinct element can be represented, that we have already seen. Okay. But you can represent m number of elements, which is m is less than r to the power n. Okay. So here you can see that 4 elements are represented in radix 2. Okay. So 4 elements can be represented by this because it is represented like this one, 0 0 0 1 1 0 and 1 1. Okay. So 4 informations can be represented by this one. So this is nothing but the binary conversion. Okay. So we can represent the information like 0 1 2 3. So these 3 informations can be represented by 0 0 0 1 1 0 and 1 1. So that is simple conversion. Okay. So only 4 informations can be represented by this way. Okay. So this is not the code word. This is not the code word. Okay. Now look at the next one. 4 elements represented in radix 2 with n is equal to 4 digits. All right. So only 4 informations are required to be represented. Let's say n1, n2, n3 and n4. So these are the 4 information that is supposed to be represented, and it is represented in 4 bit. Now if we represent it 4 bit, we cannot keep the 2 MSBs or MSB and the next MSB as 0, as blank, like rather than simply appending 0 0 here doesn't make any sense. It is not the code word again. It is simple conversion. So binary converted represented in 4 bit. Okay. So convert any particular number in binary system and represent it via k bits. That is not the code word. Okay, that is simple conversion. Okay. Now we need to have a significant representation of this particular value so that it cannot be like converted into binary and get the value. Okay. It should be a code word. Code word is representing certain hidden kind of information. Okay. So it is represented like 0001. So the first information, LSB is marked as 1. Okay. Now, second information, so second place, positionally it is marked as 1. Okay. So the first information, first place is marked 1, second place is marked 1, third place is marked 1, fourth place is marked 1. Is it a converted value? It is the code word. Okay. So you have a hidden concept in this, that the place is marked as 1. Okay. This is not the conversion. Okay. So any layman cannot easily decode such kind of information. Okay. If you do not reveal that it is hot ones is representing that the positional one is marked as 1. Okay. So the position information is marked as 1, corresponding to the first value. Okay. First value. So LSB is marked 1. Second value. So second place is marked 1. So that is called hot ones. Okay. So 8 information can be represented in 4 bit again. Okay. Or sorry, 8 bit again. Okay. In that particular case, you will have to positionally marked 1. All right. Is that clear or not? Okay. So you must have the differentiation between the code word and the conversion. Okay. Now come to this particular example. Let's say it is saying that there are over 8,000 ways. Okay. So I have just written it 8,000, but basically it is very much high, more than this. You can simply Google it. You will find the number of ways through which you can represent any particular element. Okay. So there are more than this, even more than 25,000. Okay. So I have just written it because of one literature I have. Okay. According to that, I have mentioned here that more than 8,000 ways are there that you can choose 10 elements from 16 binary bit number. Okay. And few of them I have just shown you, that we have BCD representation. Here you can see the values are differing. XS3 code. So 0 is represented like 4 times 0 in BCD, while in XS3 it is represented as 0011. And the next one, it is represented entirely different. Okay. Just look at for any other value, let's say 5 here. Now it is 8 here. 8, 4 minus 2, 1 is something different. And the gray code is entirely different. Okay. You may have the ASCII code, you may have the Unicode, you may have the different other variants, EBCDIC and so on. Extended binary coded information exchange. You must have studied in your very foundational course of information technology. 7-bit binary representation, 8-bit binary representation, 4-bit binary representation. So lots of ways are there that can be used for representing any particular information. Okay. And that is entirely different from conversion from one particular base to another base. Okay. Why it is required? Why it is required? Anyone? Why do you need different coded information to be represented for any number system? For error detection is one of the application of that. Okay. So parity coding. Okay. Gray code is also very important. The gray code also detects the error. Okay. Any other thing? Hashing, uniquely determining the location of any particular element. Okay. That is also coding, but this is not the hashing representation. That is one of these 8,000. Okay. That is one of this 8,000, but I'm just concerned about this digital logic. Okay, don't jump into data structure and other way. All right, so we'll see them one by one. Binary coded decimal. So we know that it is nothing but the 8421, and that we have seen that uh, whatever you represent in binary system, that is represented as 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. And since only 4 bits are required, so I'm just considering these 3. Okay, and if you write it like it's integer, the decimal part, so it is simply converted at 8, 4, 2, and 1. Okay, so BCD is nothing but this much. Okay, and what you have to identify, if you want to represent any particular number in BCD, in that particular case you have to simply put 1 to the corresponding place. Okay, I just want to represent 8. In that particular case, bit position 8 is going to be 1 and rest other values are going to be 0. So this is BCD information of 8. All right, it is binary coded decimal. Okay, it is binary coded decimal, so you have to be very clear that since it is the coding of decimal number system, so we cannot represent more than 9 value, more than 9. Okay, so if any value is 10 or 11 or 20, that is invalid BCD. All right, so if I write, let's say 1010, is it BCD? No, so this is not the valid BCD because it is exceeding the range from 0 to 9, exceeding the decimal range. Okay, if I convert this into equivalent decimal, it is going to be 10. Okay, so this information cannot be represented in BCD. So we have to care about the conversion. Okay, so how can we convert it, this one, into equivalent BCD? Let's say I just want to represent 10 in BCD. Ten in decimal, I just want to represent it in BCD. So we represent 1 in BCD, that is 0001. Okay, and 0 is supposed to be represented in BCD again. So this is the equivalent conversion of BCD. Okay, but suppose you have certain arithmetic operation on the BCD. Okay, let's say I have 5 in BCD, that is 0101, and again I have, let's say, 6 in BCD, 0110. This is the valid BCD. I just want to apply the addition of these two BCD numbers. That we can do. Okay, what will be the outcome? So you'll simply apply the positional sum. Okay, 1 bit sum. In that particular case, 1 plus 0 is going to be 1. Again, 0 plus 1 is going to be 1. 1 plus 1 is going to be 0. There will be a carry, and that is turned up into 1011, which is invalid BCD. How could you handle this? So you have to care about whether this sum up value is going to exceed 9 or not. If it is not exceeding 9, that is your valid sum. If it is exceeding, we must take care of this kind of values. Okay, so I'll just come to that particular value. How do we manage this? Okay, so this is the simplest code because it is not going to have any different logic that we have seen, that a hot one positional. Okay, it is simply the conversion from the positional 2 to the power value into the equivalent BCD. Okay, so this is the simplest code. Okay, you can also say it is nothing but a decimal number system conversion into binary represented by 4-bit. Okay, so 0 to 9 is simply converted into binary and represented in 4-bit. Okay, so that is why it is called as simplest code. Okay, there is no hidden logic between this. Okay, the positional one is marked as 1 only. Okay, so this is not the hot one kind of this. This is not similar to the XS3, that whatever you have converted is required to be added with the new 3 value, okay, to get the new code. All right. So it is very simple logic that you have to simply convert any number from 0 to 9 and represent it via 4-bit only. Okay. All right. So here you can see that it is having 8 plus 1, which is getting me the value 109. So it is nothing but a simple binary addition, but that could fail at this particular position, that if it is exceeding more than 9. Okay. This we have already seen how many invalid code words are there. Okay. So by 4-bit representation, we can start representing from 0 to 9, A to F. Okay. For 4-bit, you can start decoding 000 to 1001, and then 1010 to 1111. Okay. So these code words are useless. From 1010 to 4 times 1, these are the useless code words. Okay. And that is why there are 6 invalid code words. And what are the invalid code words that we have written? 1010, 1011, 101, 1100, and so on. Okay. So these are the invalid code words. All right. XS3 code. So what we are doing here, XS3 code is a non-weighted code. Okay. BCD was the weighted code. Okay. Positional weight is assigned to a particular binary number system. Okay. Now in this case, why it is called as non-weighted? Because whatever BCD value was there, that was added with a new value 3. Okay. So I am just including the next value. Okay. So just look at this. 0 is represented as 0000. Okay. So that was simple BCD. Now it is added with the new value 0011, that is 3. That is called XS3. XS3 means additional 3. Okay. Add 3 to the any existing code word. Okay. So it is going to be 0011. So the XS3 code for 0 is going to be 0011. Let's say we have 9, 1010, sorry, 101 is added with 0011, and that is going to be 0, 0, 1, and 1. Okay, just add this value 0, 0, 1, 1. Okay, and here you can see 1, 1 is 0, carry is there. Okay, so 1 and 1 is again 0 over here. The carry is produced. So 1, 0, 0 is going to be 1 here, and this is 1 here. Okay, so this is XS3 code for 1001 in BCD or 9 in decimal. All right. Okay, this is another code. 84 minus 2 minus 1. Okay, 84 minus 2 minus 1. So it says if any particular value at this particular place, let's say minus 2 minus 1, any one available at this particular place is going to be multiplied by minus 2 and added. Okay, so let's say I have 1 here, 0 here, and 0 here. So it is going to be 1 into 8 plus 0 into 4, that is 0, 1 into minus 2, that is going to be minus 2 plus 0. Okay, so resultant is going to be 8 minus 2 is 6. Okay, what was this? 10. Okay, that is supposed to be represented at 6. Okay, so in binary number system, we simply assume that this particular value is 10, but in 84 minus 2 1, it is representing 6. So for 6 you can see, okay, for decimal 6 you can see the value is represented as 1010, that we have just seen here. Okay, any other value? So just look for 9. So how 9 can be obtained from this? So this is simple arithmetic that you have to apply, that 8 plus 4 is going to be 12. Okay. 12 minus 2 is going to be 10. 10 minus 1 is going to be 9. That means each and every bit is supposed to be 1. Okay. So this is simple positional arithmetic that you can have to sum up into the resultant requirement. All right. Okay. Can you see any relation between these two numbers?
मतलब 0 का जो कोड है उसका कॉम्प्लीमेंट 9 का है, 1 का 8
Yes. So it has a relation between itself. It is called as self-complemented code. Okay. So 0 and 9, 1 and 8. Can you see? This is 0 0 1 1, and if I complement this, it is going to be 1 1 0 0, and that is nothing but 9. If you complement 1, that is going to be 1 0 1 1, which is nothing but 8 over here. The same logic is applicable over here. 8 4 minus 2 minus 1 is also self-complemented code. Okay. So pair information can be obtained from this particular code, which is representing the complemented information. All right. So this is the outcome that it has. Okay, let me hide this. Okay. So the interesting property among these two codes are that they are the complement code, gray code. So any number can be converted into gray code. Okay. What you have to do, you have to simply convert into binary and then from binary to gray. Okay. And gray is nothing but the XOR between the two adjacent bits. All right. So it is not easy that it is always XOR. First bit is, or you can say the MSB is to be taken as it is. Okay. So let me have just simple example. I just want to convert the 6 in decimal equivalent to BCD as 0110, and I just want to have the gray code. All right. How could you convert this? So what you have to do, you have to simply, okay, first drop down the MSB. Okay. And then what you have to do, you have to XOR 1 and 0, the MSB and the next one. Okay. Apply XOR on this. So if both the bits are different, in that particular case, output is going to be 1. Okay. That is the XOR logic. So in that particular way, outcome is 1 over here. Now XOR with this and next bit. This is 0 because both the bits are same. Okay. Now for the next bit, for the next position, so this one is not the correct way. This one is not the correct way to determine the gray code, because it is definitely an XOR but not from the outcome. Okay. So this procedure must be like that. Last day I told you, but you have to be very careful. Sometimes it is possible that I am making mistakes deliberately. Okay. And you have to figure it out. All right. So last lecture I have told you that it is nothing but the positional XOR, and what I am doing right now, I am adding it with the resultant value. Isn't it different from the previous one? So the correct outcome must be like this one. let me have here 0 1 1 0. 0 is kept as it is, so MSB is kept as it is, and these two bits are supposed to be XORed. Okay, the adjacent bits. XOR of this is going to be 1, then XOR of the next two bit is going to be 0, then XOR of next two bit is going to be 1. Okay, and if you follow this particular process, your outcome is going to be 0 over here, which is definitely wrong. Okay, so this process is wrong. You have to follow this one. All right. So gray code corresponding to 6, you can see it is 0 1 0 1. Okay, pick any random value and convert it. Okay, let me give you the value 1 1 0 1 1 0 0 1 0 1 0 1. Okay, convert these three numbers into equivalent gray code.
1011.
Okay, so that is not written.
1011.
Okay, first one is 1011.
Second 1101.
1101.
Third one 0111. 0111.
All right. Everyone is getting the same answer.
Sir,
So you can cross check here. 0101 is 5 and the corresponding gray code is 0111, which is just answered by you. Okay. Look at 9. 1001. Okay. The equivalent group gray code is 1101, and that you have also answered the same. Okay, is there anyone who is not able to convert this? Anyone who has any issue with converting BCD, gray, XS3 or 8 4 -2 -1? Anyone has any doubt in that conversion? Okay, shall I proceed now?
yes, sir.
All right, thank you. So like in the previous one, we have seen some special relation between the values. है ना? So what is the special property does gray code have in relation with the adjacent decimal digits? Okay, that we have written over here in two successive values. Here you can see that in two successive values, only one bit is flipped. Okay, how could you check this? Like if you look at like this one, from this particular code to this code, you can have the more number of changes. Okay, like this one, you can see that more than one bit is changed. Okay, if you look at into BCD and gray. Okay, but what you have to see, you have to see the two successive gray codes. Okay, just look at this. 0 is all 0, 1 is 0001. Okay, only one bit is flipped. Okay, now look at 1 and 2. Only one bit is modified. Okay, let's say any random value. 5 6. Only one bit is modified. Isn't it? So what we can do, we can utilize this particular property if we are consistently transmitting our information. Okay, and that particular information, let's say, have many number of bits in changes. Like here you can see that 7 and 8. Where is my pen? Okay. If I am transmitting 7 and 8 consistently, in that particular case, you can see that 4 bits are going to be changed. Okay. So it is not easy for the receiver to determine whether 1 bit is flipped, 2 bit is flipped, 3 bit is flipped, or there is certain error in this particular code. It is not easy. Okay, because entire bits have been modified. Okay. And see, if I transmit this particular information by converting it to equivalent gray code. Okay, 7 is converted into gray code and 8 is converted into gray code. Now receiver is getting this information. Okay, then it is very easy to determine whether there is a change or not. Okay, because only one bit is flipped now. Okay, if more than one bit is flipped at the receiver end, it can be easily identified that it is error, isn't it? Hai. So that is very special code that you can use in transmission of the information. Okay, just look at this particular example. It is the optical shaft encoder. You are transmitting the data through optical light. Okay, so there are actually it looks like something else. Let me have the actual representation. Okay, so here you can see that there is a code wheel, and this code wheel is actually having the gray coding logic. Okay, and this is the fixed slit that allows the rays to be passed or blocked. Okay, and the gray code is moving, thoroughly moving, either clockwise direction or anti-clockwise direction. Okay, so it permits your code to be passed or not. Okay, so some information is transmitted at any particular instant. Next time up दूसरा information send कर रहे हो. So we can easily determine that whatever information that we have sent in the previous one and send it the next time stamp, that may have only the 1 bit flip. Okay, if so, then your information is going to be almost correct. Okay, why I am saying it is almost correct? Because again, transmission medium is maybe the faulty, maybe mechanical, because it is the mechanical device, some mechanical rotation or motors are causing some noise that flips some other bit rather than the required one. So only one bit is flipped, but that is not the desired one. Okay, so it is not 100% correct. It is possible that you are getting the almost correct, the right code. Okay, so this is the counterclockwise. We may have the clockwise rotation as well. Okay, just motor rotation has been modified, but it is also giving me the same outcome. Okay, but a phase shifted. Okay, if you look at this phase, that phase has a slight shift in clockwise and anti-clockwise rotation. If I go back to the previous one, you can see the phase B is started with the, here you can see started with the 0. Okay, and if I go with the counterclockwise, here you can see that started with 1. So it has a slight phase shift in clockwise and anti-clockwise, otherwise your outcome is going to be the same. Okay, and this is very much useful in point-to-point communication protocol. Okay, point-to-point communication protocol, this open shaft encoder is used. Okay, so electronic students are very much using this kind of techniques. Okay, in electronic communication devices this is used. All right, so this you have to be very careful, that I have already discussed, that there is a difference between the conversion and coding. Okay, so conversion can be representing any particular information into binary number system with any number of bits. Okay, like 0 can be represented in single 0 bit, it can be represented in 2 bit, can be represented in 3 bit, can be represented in k number of bits. Okay, but if it is defined in coding, let's say in BCD, it is always represented at 4-bit zeros. Okay, there is no other way. If it is BCD, then 0 is represented by 4 consecutive bits, 0. Okay, there is no other way. So you can easily, uniquely decode that particular value. But in this particular case, not able to decide the. Okay, so there is very much difference between the conversion as well as in coding. All right. Now come to the binary arithmetic. All right. Do you want to have a break of 5 minutes? Okay. So we'll resume here within 5 minutes.
When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks4Geeks. When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks4Geeks. When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks4Geeks. When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks4Geeks. When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks4Geeks. When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks4Geeks. When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks for Geeks. When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks for Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch.
Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE computer science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE computer science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE computer science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE computer science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE computer science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE computer science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE computer science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE computer science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course.
Okay, so we'll start with the binary arithmetic. Online के students आ गए क्या?
Yes, sir.
All right. So we'll start with the binary arithmetic. Here we'll see the complements. That is called as like here I have written only one's complement or two's complement, but here we'll see about the radix complement and the diminished radix complement. Okay, so these two types will look here: the radix complement and diminished radix complement. Okay, why it is diminished? Because it is one lesser than the base. Okay, so radix complement, like in binary number system, it is going to be represented as 2's complement. Okay, so if you look at the radix complement, it could be the 2's complement for the binary, 10's complement for the decimal, okay, 8's complement for the octal, and so on. Okay, but if you look at the diminished one, it is going to be 1 lesser than the base. So for binary number system, it is going to be 1's complement. For decimal number system, it is going to be 9's complement. For octal, it is going to be 7's complement, and so on. All right. Then we further look at the signed binary number and how we can tackle that particular signed number. Okay, how do we apply arithmetic operation on that? Adding single bit with carry or without carry, multiple bit addition, subtraction with borrow. Okay, so single bit subtraction with borrow or multiple bit subtraction, then multiplication of the binary number system, BCD addition, and so on. Okay, so like in the previous slides, I have discussing about adding the BCD number will result you some exceeding value. Okay, so how do we tackle that kind of values? So we'll look all such information in this particular part. All right, so we'll start with the complement. So what is complement? So complements are very much useful in logic circuit design. Okay, if you want to have something opposite of any information, in that particular case you have to have the complement of the information. Okay, so like you have certain true value and you just want to have the opposite of this, so you'll simply say it is not true or it is false, which is opposite of the true. Okay, and this is nothing but the complement of true. Okay, so such information is very useful for logic circuit design, and it is because that we can have the mechanism to have the miniature of the circuit. Okay, we can have the minimum number of use of the logic gates so that we can represent the information. Okay, so complements are the alternative representation of the numbers. All right, so it is not like it is going to minimize the number of representation. Whatever number systems you have, whatever values you have, it is going to have the alternate representation. So if you have n number of informations, okay, in any number system, you have n information in the complemented one. So it is the alternate way to represent the information. Okay, it is not like that this information cannot be represented in complement, so it is reduced. Okay, so each and every value whatever is represented in any number system, that can be represented into the complement one. Okay, so it is alternate way of representing the information. So if you have n number of information, you have n complements in that particular case. Okay, so there are two types of complement: diminished radix complement, just for an example, that one's complement in binary. Okay, which is less than 1 base. Okay, so you can say it is 2 minus 1 complement. It is diminished like this. For decimal number system, it is going to be 10 minus 1's complement. It is 9's complement. Okay, and for the radix complement, it is similar to the R. Okay, it is also known as R's complement or the radix complement. So it is 10's complement, 2's complement, and so on. Is that clear? So how do we calculate these values? We'll jump to that particular part. Diminished complement. So how diminished complement is calculated? R to the power n. So here n is nothing but the mod of the number. So that is giving you the length of the digits. Okay, how many number of digits are there in the number system? Okay, so let's say you have mod n digits in your number. Okay, then r minus 1's complement can be simply represented as r to the power mod n minus 1 minus n. All right, just look at the example. For 1's complement of this particular number, okay, how many bits are there? 3, 3 and 1. So 7. Mod of this particular number is 7. Okay. So just apply the formula here. 2 to the power 7 minus 1 minus this value 10101111. 2 to the power 7 is nothing but 1 followed by 7 times 0. Okay, 1 followed by 7 times 0. You just simply write the positional power. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3 and so on. So 2 to the power 3 is 1 followed by 000. Isn't it? So 2 to the power 7 is 1 followed by 7 times 0 minus 1. What will be the value corresponding to this? This one is 8. 2 to the power 3 is 1 followed by 30 which is equivalent to 8. Okay. और इसमें से एक रिड्यूस करें तो 7 है ना, minus 1 is 7 and that is simply 111. Okay. So what we can write for this? 7 times 1 only. Are you getting this point? No. Just look at this value 2 to the power 0, 2 to the power 1, 2 to the power 2, 2, 3, 2 to the power 4, 5, 6, 7 and so on. Okay. So if you want to write any particular information 2 to the power 7, that should be 1. Rest other value is going to be 0. So I just kept it 0 over here. Okay. And I just want to reduce this by 1. If I reduce this by 1, that is going to be all 7 times 1. So every 0 is simply converted into 1. All right. Got this? Now you have to subtract your information, that value 1010111. That value was given in the previous example. If I subtract this, it is going to be 0 here, 0 here, 0 here, 1 here, 0, 0. Sorry, this would be 1 and 0. That's it. So this is the actual logic to convert any information into one's complement. और हमने क्या प्रैक्टिस किया हुआ है? Just flip the bit, toggle the bit. है ना? That is also correct. That is the shorthand to get the ones complement of any particular information. We have just flipped the bit. 0 is converted into 1, 1 is converted into 0. So we have just flipped the bit. And it is possible because of this particular property. Okay. Now what about 9's complement? Let's say I just want to have the 9's complement. 9's complement of, let's say 3, 4, 5 base 10. How many number of digits are there in this example? 3. Okay. So we have to compute 10 to the power 3 minus 1 minus the value 3, 4, 5. Okay. So 10 to the power 3 is 10,000 minus 1 minus 3, 4, 5. So 10,000 minus 1 is going to be, okay, This should be 1000. 10 to the power 3 is 1000. Okay. So this is going to be 1000 minus 1 is going to be 999. Minus 345. That is 654. Are you getting the same? So what is the shortcut method to find r minus 1's complement for any radix? Let's say I have information like 1, 2, 3 base 5. Okay, I just want to have the 4's complement. Just look at this. For 1's complement, I have subtracted the information of equivalent length of all ones. I have subtracted equivalent length of all 9 for 9's complement. For 4's complement, what I do? Equivalent length of 4 subtracted by the value. So it is going to be 3 to 1. Isn't it very easy? So any diminished radix complement can be easily calculated by having the equivalent length of diminished radix, okay, and then subtract the given number. Okay, so 7's complement, 15's complement, and all you can easily do. Okay, so just look at the information over here. 9's complement of 5, 4, 3, 2, 1. Equivalent length 5 times 9 minus 5, 4, 3, 2, 1, which is going to be 4, 5, 6, 7, 8. All right. Any doubt? Anyone has any doubt? All right. So we'll go for the radix complement. So radix complement, that means equivalent to the base. So 2's complement, 10's complement, 8's complement, 16's complement, and so on. Okay. Or for any unknown radix r, it is r's complement. Okay. So r's complement can be easily calculated by r to the power n minus n. Or you can simply say it r minus 1's complement plus 1. That concept we have already seen for the 2's complement. Just have the 1's complement and add one more 1. That we have seen. Say for this one, 2's complement of this particular value. Okay, so I have used this particular method, that 2 to the power the length of this. Okay, so 2 to the power 7 subtracted with this. Okay, so it involves, this particular method involves the subtraction. Okay, but what we can do by other way, we can simplify the 1's complement for the given number, and 1's complement for this particular number is 0, 1, 0, 1, 0, 0, 0. Okay, and in that particular case, to get the 2's complement, simply add one more bit in LSB, and that is going to be 1, 0, 0, 1, 0, 1, 0. So this is 2's complement, and you can check this is same, which is computed by the formula and the shorthand. All right, so in r's complement, you have to be careful about the borrow from every position. Okay, But in case of r minus 1's complement, it is very easy to calculate. Okay, let's say for this 10's complement, I just want to find the 9's complement. So 9's complement can be easily computed like, since it is 5 digits, so 5 times 9 subtracted by this particular value 1 2 3 4 5, and it is very easy to subtract from this rather than subtracting 5 from 0 or 4 from 0 and so on. Okay, so we can easily compute the value over here. It is 4 5 6 7 8, and simply add one more to the last bit, last digit. In that particular case, it is going to be 87655, which is nothing but the same. Okay, so you get the tens complement of this particular number. Okay, so follow only one technique, either the formula one or the shorthand. Compute the ones complement or r minus 1's complement and add 1 to get the r's complement. Okay, whether your base is known to you or unknown to you. All right, so let me have few example for you for the practice. Find 4's complement for 2034 base 5. Okay, question is gone. Let me write it again. 4's complement for, what was the question? 2034 base 5, and the second question is 7's complement for 1266 base 7. Which one is the diminished radix complement and which one is the radix complement? 7's complement is diminished. You have to check the requirement as well as the base. Okay, so 4 is 1 lesser than the base. Yes, 4 is diminished and 7 is the radix. Okay, for 4's complement, it is 2410. 65. So let me solve this so that you can check the value. 4's complement, so it is going to be 4 times, because the length of this particular number is 4, and subtracted the given number, and it is 0 1 4 and 2. So this is going to be the correct for this one. For this, we have to compute the 7's complement. So what we do?
4 times 7 is subtracted with plus 1.
Okay, so you just want to have the r minus 1 complements. So in that particular case, you have to apply 6666. If you want to apply r minus 1 complement then plus 1, then in that particular case you have to go for 6666 minus 6, sorry, this 1266, and in that particular case outcome is going to be 0 0 4 and 5. Add one more to get the, so it is 6 complement. Okay, this value is the 6 complement. To find the 7's complement, you have to add one more to this, so answer is going to be 5401 in this particular case. So this answer is incorrect. Or what we can do, we can simply apply 7 to the power 4 minus 1266. Try it. You have the calculator, just try it. Compute 7 to the power 4 minus 1266. Give me the answer.
2401. One one three five. 1135.
How you are computing 7 to the power 4? Okay. 11. 1135. So it is giving you 11354 here. Okay. By the formula, it should be, if you look at the formula, that is going to be the radix to the power number of digits minus the value. Okay. But if you look at this diminished radix complement, it is going to be one lesser value from the base. Okay. So that is going to be 6. That appearance number of digits. Okay. So 6 4 times subtracted with the value, whatever is the outcome added with 1 is going to be the 7th complement. Okay. So according to me, this is the correct one. हाँ, ये base 10 में आएगा. That is going to be the wrong. Okay. That is why because whatever value you are calculating 7 to the power 4, that converted value is given in base 10. Okay. So this is not the right representation in base 10. No, sorry, not in base 7. Okay. So this information is not written in base 7. Are you getting my point? You have calculated 7 to the power 4 and that particular value is in base 10, not in base 7. Okay. So first you have to convert that value into base 7 and then you have to apply the subtraction. Okay. So that was a little trick. That's why I told you how you are calculating 7 to the power 4. Okay. So for any unknown base, you cannot directly get the power of that base and to have the value. Whenever you take r to the power any number, that will result you in base 10. Okay. So you have to convert that particular value into base 7 and then apply the subtraction so that you will get the corresponding base required base. Okay. So rather than jumping into that particular conversion system, this shorthand is going to be the better one. All right. So just find the complement for this. Subtract this particular number 72532 minus 72 3250 using tens complement. Okay, so if I simply use decimal number system to apply this subtraction, I'll just simply subtract this particular value as 72532 minus 03250, and the outcome is there as 2. It will take a borrow from this one, so it is going to be 13 minus 5, that is 8, and this is going to be 4. Result is 2. Now it will again take a borrow, that is going to be 12, minus 3 is 9 here, and this is going to be 6. Okay, so this should be the subtraction result, but it says not to apply the decimal arithmetic. It is saying that solve this particular question using tens complement. So do we need to take the tens complement of 72532? Okay, are you able to solve this question? Okay, let me solve this first, then I'll come to the next question. Okay, for any negative representation or any negative number, the r's complement plays the important role. Okay, take the r's complement of negative number and add with the first number, you'll get the same result as subtraction. Okay, so if I take the tens complement of 3250, okay, just find the tens complement of this. It is going to be 9999 minus 3250 is 9, 4, 7 and 6, added 1 to get the tens complement, so it is going to be 6750. All right, or what you can do, since it is of 5 digit, first it should be padded with 0 to make it uniform. Okay, so before applying any particular operation, you must make all the numbers into uniform representation. Okay, so it is represented in 5 digit here, so this outcome is going to be 96750. Is that okay? Now what we have to do, we have to add this particular number with 72532. So just add this 96750. If I add this, it is going to be 2, 8, 7 plus 5 is 12, 1 carry is there, 6 plus 3 is going to be 9, and 7 plus 9 is going to be 16. So here you can see that there is a 1 carry. Okay, in r's complement operation, if there is a carry, then your result is going to be positive. Okay, ignore the carry and mark as result is positive. Okay, and whatever is the outcome is your result. Isn't it same that we have found through the subtraction? Got it or not?
Yes, sir.
Okay. So for any negative number operation or any subtraction, you have to convert that particular negative number into the r's complement and then simply add. Okay. You have another question. How -5 is represented in memory? Let's say in memory it is represented by 8-bit. Okay, your memory requires to be represented by 8-bit binary number. So how 5 -5 is represented in memory?
1000101.
Let me write it. 1
Triple zero
000
zero
101. Okay. So what you did, you just find the 5 and MSB is placed at 1. It is representing the negative number, isn't it? That mechanism you have applied. Okay, any other answer? So I'll throw a party of coffee, those who will answer correctly. So one coffee from my side. हाँ 8-bit ही है नहीं overflow we cannot apply overflow. MSB is representing the sign bit. Okay, if it is 8-bit representation, then MSB is going to be the sign bit.
Sir, it's 4 zeros.
1 4 zeros followed by 101. Triple one. Okay, your answer is 1 4 times 0 triple one. Interesting. That is entirely different from the previous one.
4 zeros, sir.
Okay, 4 zeros. I'm not sure it is correct. Yeah. 0 triple one 1011. MSB is 0. ऐसा कहाँ है? टूज कॉम्प्लीमेंट किसका लिया है? -5 का. Okay, let me solve it for you. Okay, 5 can be represented the magnitude. Okay, just take the magnitude, represent it as simple binary number system. Okay, so it is going to be 101. Since it is 8-bit requirement, append all zeros before this. Okay, so this is the equivalent binary of +5. Okay, now to represent any negative number in memory, it must be represented by 2's complement. Okay, so just get the 2's complement of this particular number. It is going to be 1 1 1 1 0 1 0. That is the 1's complement, and just adding one more bit in the LSB, it is going to be 2's complement. Okay, so -5 in memory is going to be represented by this value. It is 5 times 1 followed by 0 1 1. Okay. So any negative number in memory is represented by its 2's complement. Okay. So first you have to find the 1's complement of the magnitude represented in binary number system. ठीक है, और आपको डिजायर्ड जितने भी बाइनरी बिट्स चाहिए उतना आपको अपेंड करके 0 कंप्लीट कर लेना है, अदरवाइज योर आंसर इज गोइंग टू बी रॉन्ग. Okay, if it is 8-bit representation you have to represent it by 8-bit. Okay, then find the 1's complement and then find the 2's complement. Now here you can see since MSB is 1, it is a negative number. All right, any doubt? Anyone has any doubt in this? All right. So signed binary number, the sign magnitude is represented in most of the cases that MSB is representing the sign of the number. Okay, in any particular case, MSB is represented by the sign. Okay, while the remaining bits represent the magnitude of that particular number. Okay, positive numbers have a 0 here at the MSB and negative number has the 1. We have just seen the example, -5 and +5. Okay, in both the cases you can see for +5 you have MSB as 0 and for -5 your MSB is 1. Okay, so sign magnitude simplifies the arithmetic operation but requires additional logic to handle the sign, because we cannot modify the sign value. Okay, if two numbers are operated, their sign must be, the required resultant sign must be represented at that particular bit. Okay, at MSB. And suppose if there is any carry at MSB or any borrow is required at MSB, how do you handle that? That is extra bit apart from sign, and one position cannot handle 2 bits. One position can only represent single bit. Okay, so how could you handle that particular extra bit? No sign, we cannot change the sign. If we change the sign, the entire value is going to be modified. Na? We cannot change the sign. That is why I told, just written over here, required additional logic. So have you heard about the overflow flag? Some flags are there in the microprocessor microcontrollers to handle such kind of information. Flag register. Okay, so that flag register vary in number of bits depending upon the architecture. Okay, it may have the sign flag, it may have the 0 flag, it may have the parity flag, it may have auxiliary carry flag, it may have the overflow flag. That overflow flag handles such overflow information required due to carry or borrow. Okay, if so, that particular bit is represented by overflow flag, sign bit is represented by the MSB. Okay, you cannot modify that. Clear? All right, let's say I just want to have the 2's complement of -13. So process is very easy. First you have to find the magnitude, find the 1's complement of the magnitude. Okay, then find the 2's complement of the 1's complement, converted 1's complement. You'll get the resultant value for signed number. All right, so -13, so 13 is represented by 0 1 1 0 1. Find the 1's complement and then you'll get the 2's complement. Okay, now in this case you can see that I have taken one additional bit over here. 13 can be represented by simple 4 bit, na? If you get 1's complement for this, it is going to be 0 0 1 0, and 2's complement is going to be 0 0 1 1, है ना? Then in this particular case your sign is missing. Okay, what happens? Okay, so in this particular case you can see by using that much representation, which is the minimum requirement for that particular representation of the magnitude, will lose the sign bit. Okay, for that either we have to represent it by the minimum required information, 8 bit, 16 bit, 32 bit, or we simply add one additional 0 over here. We simply add 0 over here for maintaining the sign information. Okay, clear? So since it is positive 13, we can say it is 0 1 1 0 1. Okay, now take the 1's complement of this, it is going to be 1, and then get the 2's complement, it is going to be 1 0 0 1, and now this is the representation of minus 13, and MSB is maintaining the sign. It is 1, that means negative number is. All right. Okay, let me have this particular question. I have 2's complement represented by this. What is the magnitude of this particular value? Just find the magnitude of this. साइन बिट हटा दें, बाकी जो बचा उसको बोल दें मैग्नीट्यूड है. इसका फिर से टूज कॉम्प्लीमेंट लेंगे, रिवर्स प्रोसेस करेंगे. विल नॉट गो फॉर द टूज कॉम्प्लीमेंट, विल रिवर्स द प्रोसेस. सबट्रैक्ट 1 and toggle the bits. Okay, if you want to find the magnitude of any given 2's complement, then you have to have a subtraction of 1, okay, and then find the 1's complement of the subtracted value. That will result you the original magnitude. Just check it. 1 0 0 1 1 subtracted with 1, okay, it is going to be 1 0 0 1 0, and now get the 1's complement of this, 0 1 1 0 1, okay, which is representing the magnitude, that is 13. All right, so such kind of questions were there in the GATE exam, that you have given a large number as a 2's complement, okay, and you have to find the original magnitude of that. All right, I'll come to that particular question. Let me have this question right now. It is question asked in set 2 of the GATE exam 2016. Let x be a number of 16-bit integer, okay, distinct 16-bit integer in complement representation. All right. The question is, x is represented in its complemented information. Okay. Now, y be the number in the distinct 16-bit signed magnitude representation? So, what will be the value of x minus y? Question is clear or not? Please read the question and let me know whether question is clear to you or not. I am not getting any response. No? No? No response? Okay. So I'll consider it that they are not able to get the question. Okay, let me have the example over here first. Let's say I have any number which is represented in 2-bit binary. Okay, I'm just simplifying this particular question for you. If 2-bit representation in binary number system, it is simply 00011011. Okay, what will be the ones complement of this? It is going to be 11, 10, 01 and 00. What about the 2's complement of this? It is 01. Sorry, this is 00. Okay, and this is 11, 10 and 01. Okay, that means if it is of 2-bit, how many numbers are represented? 2 to the power 2. And how many complements are there? 2 to the power 2. Okay, यहाँ तक clear है? So if it is of 16-bit representation, that means total possible numbers are 2 to the power 16 and its complement count is going to be 2 to the power 16 for any n-bit distinct numbers. Okay, possible numbers are 2 to the power n. Okay, and since complements are the alternate representation only, okay, they are not the replacement, they are the alternate representations only. That means for n distinct numbers there are n distinct complements. Okay, that means the total number of elements in the complement is going to be 2 to the power n again. All right, now look at for the signed number ranging from minus n to plus n. There comes a value 0. 0 is non-negative, non-positive. है ना? So if there are total possibility to have 2 to the power n for unsigned number, for signed number it is going to be 1 lesser than the total length. है ना? So total number of values corresponding to signed numbers are going to be 1 lesser than the total existence. All right. Now come to the original question. X is representing 2 to the power 16 possibilities to have the complemented value because it is represented in 16 bits. Okay. Y is the same but in signed information. That means it is going to be 2 to the power 16 minus 1 and it is asked to compute x minus y. So it is 2 to the power 16 minus 2 to the power 16 plus 1. Okay, so this has to be cancelled out and your outcome is going to be 1 only. Very simple question. But that has to be logically think. Okay, so complements are nothing but the, so whether it is complement, it is BCD, it is XS3, all these are the alternate representation of any number. Okay, that is not the certain kind of replacement with the miniature values, or certain codes cannot be, certain number system cannot be represented into the corresponding code. It is just a replacement. Okay, so the count will not be decreased or increased. Okay, whatever is the original range, that is going to be represented in the alternate representation. So in complements, this is going to be the same. It is going to be 2 to the power 16. Okay, and for signed number, you have to care about the 0. Okay, your 0 is neither representable in negative or positive. So total number of appearance going to be 2 to the power 16 minus 1, or 2 to the power n minus 1. In that particular case, you can simply have the subtraction. So 2 to the power 16 minus 2 to the power 16 minus 1 is going to be plus 1, and that is answer is plus 1. Is that clear to everyone? Please respond. Yes or no? All right. So rather than 16-bit, it could be 32-bit, it could be k-bit, it could be random value, but your logic should be the same. Okay. Next question from same exam, but set 1. GATE 2016, set 1. A 16-bit 2's complement representation of an integer is given to you. So this is the 2's complement representation of any number. Its decimal representation is, that means the requirement is you have to find the magnitude in decimal representation. I told you how to convert this. It is 2's complement. Apply the reverse process to get the magnitude. Okay, and just tell me the answer. Seven. Let me compute. 11. 11 base 10. Okay, let me do this. So let me subtract 1 first, and then it is going to be 0 here. So it is 0, 1, 0. All right. All are ones. Just have the ones complement of this. So it is going to be 0, 0, 0, 0, 0, 0. Again 0, and it is going to be 1, 0, 1, 1. And this is, yes, 11 base 10. Right. It is 11 base 10.
2's complement का एक बार और 2's complement लेने से भी same thing होता है।
इसका 2's complement एक बार और ले लिया जाए. So it is 1, 1, 1, 1. Sorry. First you have to go for the 1's complement. So it is going to be all zeros. And then plus 1, it is going to be 1, 0, 1, 1. And that is having 11 base 10. Yes. क्यों आता है? Okay, I'll again come to this particular topic in XOR gate. Okay, so XOR gate has a very beautiful operation, or you can say the complement has a very good nature. Boolean algebra के अंदर I'll cover that particular topic again, that A can have the complement as this much, and if I apply the next complement of the complemented value is giving me the same information. Okay, so that is the duality principle of the complement. Okay, so complement of complement will give you the same result. Okay, so that is one identity under the Boolean algebra. Yes, is that clear? Go to the next one. In 16-bit 2's complement representation of the decimal number minus 28. So just let me know the procedure.
प्लस पॉजिटिव को बाइनरी रिप्रेजेंट करके फिर उसको
प्लस 28 या 28 का बाइनरी रिप्रेजेंटेशन करेंगे इन हाउ मेनी नंबर ऑफ बिट्स? You have to be very careful about that. 28 can be simply represented in 5 bits. Okay, so you have to append zeros before that to get it complete 16-bit information, and then you have to find the 2's complement. Okay, do it.
ऑप्शन सी
Option C. Please write your correct outcome as an option in chat box. Option A or B or C or D. Okay, I'm getting option C as your response. All right, that is the correct outcome here. Option C. Are you getting the same? Are you getting the same answer? No? Let me see the. नेगेटिव वाला नहीं समझ में आया. लेट मी हैव दिस. आपका क्वेश्चन क्या है? -28. -28 का रिप्रेजेंटेशन ये तो नहीं है. हाँ देखो क्या है, 1 2 4 8 16 32. ये रिप्रेजेंटेशन होता है ना, 2 to the power 0, 2 to the power 1, 2 to the power 2 and so on. 28 कैसे आएगा? 16 plus 4 is 20 plus 8 is 0 0 कर लो. इसके पहले अब आपको 16 बिट करने हैं. 4 4 8 16 हो गया. नाउ गेट द वंस कॉम्प्लीमेंट. ठीक है, वंस कॉम्प्लीमेंट क्या करेंगे? टॉगल ऑल द बिट्स. सो 1 then 1 0 0 0 1 1. For 2's complement, add one more over here. It is going to be 1 plus 1 is 0, 1 carry. 1 plus 1 is again 0, 1 carry, and this is going to be 1 0, and the rest thing is same. Check the answer here. Okay, clear abhi? So anyone from online who is not able to solve this, please let me know. So this is the learning phase. Don't feel shy that class has a number of students or it is live. Don't feel awkward, don't feel shy. Okay. Okay, so I'll consider it as your acceptance that you have learned the concept. I'll proceed further. Addition and subtraction using 2's complement. Okay, for any signed binary number. Okay, so for any signed binary number, we can apply the addition or subtraction using 2's complement. Like in previous example, we have seen subtract two numbers via 10's complement. Okay, so for addition, there is no problem. If positive numbers are there, there is no need to convert into 2's complement, because 2's complement is only required for negative number representation. I told you earlier. Okay, so once you represent any negative number in 2's complement, again in that particular case you need not to subtract. Though it is subtraction, you have to simply add. Okay, are you able to get my point? If it is positive sign number, then simply apply the addition or subtraction. Okay, need not to care about the complement. If it is negative number, in that particular case you have to find the 2's complement and add that 2's complement with the augment. Okay, you need not to subtract because you have already included that sign into the binary number system representation. Okay, so you need to simply add that particular value. Let me have this example here. I just want to subtract 2 from 5. Okay, so what I can do, I can have 5 plus minus 2. Can I write this? Okay, now I can represent 5 into the binary and it is nothing but 0 1 0 1. Okay, I can represent minus 2 into binary. Okay, why? By 2's complement, by using 2's complement. So 2 is represented in binary as 0 0 1 0 and its 2's complement is going to be 1 1 0 1 added with 1, it is going to be 1 1 1 0. Okay, so this is the 2's complement of minus 2. So I'm just placing the value of 2's complement, that is 1 1 1 0. Now what is the sign between these two numbers? What is the current sign between these two numbers? Plus. Addition. So I just need to add these two values. Okay, so add these values. 1 0 plus 1 is 1, 1 plus 1 is going to be 0 and 1 carry over here. Okay, add this particular carry with the number, that is 1 and 1 is going to be 0 here and there will be a carry. Okay, ignore this carry, just have the value. Okay, I just told you, if you apply the arithmetic operation with the complemented information, ignore the carry, and if there is a carry, that will represent the positive outcome. If you can recall this previous example, let me go back to the previous example. Here, if there is a carry, your result is going to be positive and ignore the carry. Okay, that was the tens complement. Now I am using ones complement here, and I told you just apply the addition, and if you get the carry, ignore that particular carry. Okay, and your outcome is going to be positive. So from this particular example, you can see that 5 has the higher magnitude than 2, and if I subtract 2 from 5, my outcome is should be plus 3, and that is I am getting over here. All right, let me have another example. 5 minus 8. Okay, that is not given over here. Just try to solve it. 5 minus 8. I know the outcome should be minus 3. So apply the same concept. 5 plus minus of 8. Okay. 5 is represented as 0, 1, 0, 1. Find the 2's complement of 8 so that we can have the minus 8. Minus 5, minus 2, I'll come to that. Give me the 2's complement of minus 8.
One one triple zero, sir.
1, 1, 0, 0. Add it. So this 1 is required. If I am dealing with 4-bit binary representation, this 1 will play the role over here or not? Okay. So since we are taking the 2's complement for 4-bit binary, this 1 is going to be ignored. Okay. Your outcome for this is going to be 1,000,000, and that is added with this particular number. Okay. Once you add this, your outcome is going to be 1101. There is no carry. There is no carry. That means your result is negative. Okay. And to obtain the actual result, to obtain the magnitude, what you have to do? Just take the 2's complement of the outcome. To get the magnitude, you have to apply the 2's complement. Okay. What will be the value? 0, 0, 1, 1. And that is going to be minus. So that is going to be minus 3. Is that clear? Anyone has any doubt? Anyone has any doubt in 5 minus 8? So I have taken this 8 deliberately to show you this particular example, that if you get one additional or extra one than the normal representation, okay, you have to ignore that. Okay. And whatever is the required number of bits to be added with the augment, you'll get the result. Now result is having no carry. In that particular case, you are able to decide that result is going to be negative. Okay. And whatever is the outcome, if you want to know the magnitude of that particular outcome, just take the 2's complement again for that particular number, you'll get the value. Okay. You'll get the magnitude. So 5 minus 8 is going to be minus 3 by this way also. Okay. By the bits representation, you may be not able to decode it easily because it is not written in normal binary number system. It is the 2's complement of the outcome. Now let me come to this particular question. It has a doubt. If I write this like 1, minus 5 minus 2 can be written as minus 5 plus of minus 2. And I just told you in previous example that any negative number can be represented as 2's complement. Okay, whenever you store this particular value, whenever you transfer this information to your CPU for calculation, that is either going to be stored in your permanent memory, that is going to be stored in RAM, or that is going to be stored in registers. Okay, without loading that particular value, you cannot apply the operation. Okay, so once it is loaded into the register also, your negative number is going to be converted into 2's complement. So just find the 2's complement of -5, 2's complement for -2. Okay, just find the 2's complement of these two values. And here we have the value, that is 1011 for -5 and 1110 for -2. Got it? Now apply the addition, because there is addition sign in between these two negative numbers. So apply the addition. 1 and 0. 1 added with 0 is 1. 1 added with 1 is 0. There will be a carry. Okay. Now 1 added with 1 is again 0. There will be a carry. 1, 1, 1. 3 times 1 added is resulting 3, and equivalent binary is 1, 1. Okay. So 1 is carry over here. If there is a carry, that means we have to ignore this. Okay, and your result is 7 over here. All right. So we start with, like, every time during the arithmetic operation, we need to handle the addition of binary numbers. Okay, it is going to be 2-bit binary addition or 3 bits at a time. Okay, initially you are taking, let's say in this particular example, initially you are just adding two numbers, 2 digits. Okay, but whenever there is a carry, in that particular case you need to handle 3 bits. Okay, so we simply assume that we are just trying to add 3 numbers, whether this is going to be the carry, this is n1 and this is n2. Okay, now carry is either 0 or 1. When you do not have to take any particular carry for the least significant bit, you can simply assume that carry is always 0. Okay, and for other cases there may be a carry or may not be. Okay, so we can assume simply that we are adding 3 bits where carry is 0 or carry is 1. Okay, so in case of binary addition, we can simply assume that whether carry is 0 or carry is 1. All right, so just look at the possibility that if we want to add 0 with 0 and carry is 0, what will be the outcome? Sum is 0 and there is no carry produced by this, so this sum is going to be 0 and carry is going to be 0 again. Okay, let's say I just want to have x as 0, y as 1 and carry is always 0. That is why I have not written carry column in this particular case. Okay, because carry is always 0. Okay, so if I add this particular number, then outcome is going to be 1, sum is going to be 1 and carry is going to be 0. So I just put sum over here and carry is 0. Okay, go for 1 0. The same case, sum is going to be 1, carry is going to be 0. So it is sum is 1, carry is 0. Okay, and for 1 1, the earlier carry is 0, then in that particular case sum is going to be 0 and carry is 1. So it is going to be represented like this one. Okay. And if you solve this particular equation by K-map, I'll come to this particular topic again in the next lecture. How do we minimize the structures? So if we solve this, it is going to be x bar x, y bar y, and just write the values corresponding to this. This is going to be 0 0, this is going to be 0 1, 1 0, and 1 1. Okay, just look at the corresponding value of sum. For 0 0 it is 0, for 0 1 it is going to be 1, for 1 0 it is going to be 1, and for 1 1 it is 0. If we simplify this, what you are getting? X complement y plus xy complement. Okay, so sum is nothing but the XOR. Sum is nothing but the XOR. Okay, so if you supply 2 bits x and y, apply XOR gate to get the sum. Okay, just go for the carry. If I apply the same concept for the carry, it is going to be 0 0 0 and 1 only here, and this is x and y. So carry is going to be AND. So this is applied with the AND operation to get the carry. Okay, this is for single bit addition without carry. Okay, now we can have the previous carry. Let's say I just want to have the single bit addition, but the carry is always there. Okay, all right. So we do have already written something. Let's say z is always 1 and x and y can vary for 0 0 0 1 1 0 and 1 1. All cases are there. Just have the addition. 0 0 included with the carry, sum is going to be 1, carry is 0. Okay, so in this particular case, sum is going to be 1, carry is 0. Okay, for 0 1 1, so in that particular case it is uh, 0 1 1. Second case is 0 1 1. X is 0, y is 1, carry is 1. Okay, and if you add this, 1 and 1 is going to be 2. 2 is nothing but 1 0. So 0 is the sum place, 1 is carry. Okay, so sum is going to be 0, carry is going to be 1. Okay, now go for the next case. 1 0 1, it is going to be sum is 0, carry is 1. And for 1 1, and with the carry 1, it is going to be 3, and that is simply represented as 1 1. So 1 is the sum and 1 is carry over here. So it is this much. Okay, now if you apply the K map, find the logic diagram for this one. Just find the logic diagram for sum and carry if carry is 1. What should be the K map size? You can represent it horizontally or vertically. That depends upon your requirement, what you feel comfortable. I'm just writing it as x complement y, sorry, x complement x and y complement z complement, y complement z, or yz, yz complement. Or what you can do, you can like it x complement y complement, x complement y, xy, xy complement, and this is going to be z complement z. Okay, so that depends upon you. Doesn't matter कि आप कौन सा method use कर रहे हो, ठीक है, horizontal or vertical representation of this, answer will be the same. Zero zero one, sum is going to be 1 over here. Then for all triple one, sum is going to be here. Okay, so it is going to be x bar y bar z plus x y z. Okay, or we further simplify this. I can see the simplification possibility over here. If you can further go, it is going to be x bar y bar plus x, sorry, x y and z. Okay, ये कौन सा गेट है? x complement y complement plus x y. So this is your sum, and similarly you can solve it for the carry also. Okay, so I'm not wasting this time for circuit diagram because that will come again in combinational circuit. Okay, combinational logic design. So I'll skip this particular part over here, and this will be known to you. This is very familiar uh, gate. Huh? NOR, XNOR. Okay, so I'll recap that particular part again. So what is AND or NOR gate? What are the universal gates, and how we can represent the other information? So I'm just skipping this particular part over here. Addition is clear or not? Okay. Now, since it is arithmetic operation, so I'll jump to the next particular part. Okay, my pen is again disturbing. Okay, multi-bit binary addition. In that particular case, the LSB is always treating carry as 0. Okay, if you have to add the multiple bits, in that particular case, the LSB is always treated as 0. Okay, because there is no previous carry from any particular point. Okay, now add this particular information 0 0 1. Okay, so this is addition of 2 bits with carry is 0. Okay, so there we can see that some result is some result is going to be 1 here, and carry is going to be 0. Okay, so it is again addition with carry 0. 1 1 is going to be 2, and that is nothing but 0, and carry is 1. Okay, 1 1 1. So it is 1 1 is going to be 1 0 plus 1 is going to be 1 1. So 1 is sum and 1 is carry. 1 0 is 1, again 1 0 is 1. So sum is 1 here, carry is 0. 1 1, that is going to be sum is 0 and carry is 1. So this is the outcome, that 1 0 1 1 0 1 is the sum of this particular value. Okay, similarly you can go for the second example, that you have to add 0 1 1 0 0 with 1 0 0 1. So let me have the answer.
Triple 1 0 1.
Triple 1 0 1, because every time there is no carry produced. Okay, so it is not causing any effect on the multibit. So it is quite simple example. Okay, now single binary subtraction. If you want to have the subtraction in the binary, so again we can treat that there is a previous borrow and there is no borrow. Okay, if you want to subtract x and y, okay, you can simply consider that there is previous borrow or no borrow. So in both the cases, just look at the example that borrow is considered as 0 in the first case, and in that particular case we can have the simple subtraction 1 minus 1 is going to be 0. So subtraction result is going to be 0 with borrow is 0. Okay, 1 minus 0, then subtraction result is 1 and borrow is 0. Similarly for 0 minus 1, and in that particular case you have to take 1 borrow, and because 1 cannot be subtracted from 0, so you have to take borrow from the next candidate. In that particular case borrow is going to be 1 and this result is going to be 1 0. If you take one particular borrow here, in that particular case it is going to be, so here we can say it is 2 to the power 0, and if you take any particular borrow from the previous candidate, it is going to increase the power over here. Okay, so it is going to be 2 to the power 1, and 2 to the power 1 is nothing but 1 0. Okay, and if you subtract 1 from this particular number, your subtract result is going to be 1. 2 minus 1. Okay, तो ये बहुत केयर करने की जरूरत है. Whenever you take borrow, you are taking the radix from the previous candidate. It is not 1. It is not 1. If you just consider the decimal number system, let's say 985, and you want to subtract 079. So you are taking one particular borrow from this one, na? Okay. Was it 1 only? That was 10. You are taking the radix equivalent borrow. Okay. So it is going to be 15. Now you can subtract. If you take only one borrow, then it is going to be 6 only. Okay. So it is the base equivalent borrow. Okay. So in this particular case, again, if you are taking base equivalent borrow, then it is going to be 2. So 2 into 2 to the power 0. If it is multiplication of these, it is going to be 0 plus 1. Base is going to be, that power is going to be added. Okay. So your new power is going to be 2 to the power 1, which is equivalent to 1 0. And if you subtract anything from 1 0, that is 1, your result is going to be 1. 2 minus 1 is 1. Okay. And you have taken borrow, that's why borrow is 1 here. All right. 0 minus 0, there is no borrow, no result. Clear है ये? Okay. So just go for the multi-bit subtraction. So I'm extending this to multi-bit subtraction. Initially, again the same concept. LSB will represent the 0 borrow. There is no borrow for LSB initially. Okay. Now just want to subtract this. 0 subtracted 0. Result is 0. There is no borrow. Okay. Now 1 subtracted 1. Result is 0. Again there is no borrow. Okay. 1 minus 0 is going to be 1. 0 minus 0 is 0 because there is further no borrow. Okay. 1 minus 1 is going to be 0. So this is the subtracted, or you can say the difference result between the minuend and the subtrahend. Just look at another example. I just want to take borrow in this particular case because we cannot subtract 1 from 0. Okay. So if I take one borrow from this one, this number is going to be 0, and it will borrow to the next one, it is going to be 1 0. 1 0 minus 1 is going to be 1. Okay, and now it is converted into 0 because it has already given its magnitude. Okay, it has to take borrow from the previous one. Whenever it gives borrow, it is going to be reduced by 1, so it is 0, and this is going to be 1 0. Okay, so 1 0 minus 1 is going to be 1. 1 0 is 2. Okay, 2 minus 1 is 1. Okay, so that is 1. Now there is no value at this particular place, so 0 minus 0 is going to be 0, 0 minus 0 is going to be 0, 1 minus 1 is going to be 0. Okay, let me have one more example. Apply subtraction and find the result. Okay, without considering who is greater or not. Minute is greater or subtrahend is greater in this case? Let me have the BCD. Okay, let me have the BCD representation of this. It is going to be 6E, and it is going to be 7 3. Which one is greater? It is not necessary to convert into the decimal one only. Okay, by this BCD representation I can say that 7 3 is much greater than 6E. Okay, so you have to be very careful about this whenever you are subtracting. In that particular case, here you can see the note. If the subtrahend is greater than the minute, interchange. That means you have to apply subtraction from this one. So you have to subtract 0 1 1 0 triple 1 0. Okay, you have to apply subtraction between these two, and whatever is the result, you apply negative with this. Find the subtraction result and then apply negative with that. Are you getting the same outcome? No? Okay, so let me solve it for you. Just let me know. Write down the numbers. I just need your these numbers. Okay, tell me the number.
0,
0,
111,
111, 00,
00,
111. Okay, the next number.
0,
0,
11,
11,
0, 111, 0.
okay. I just want to subtract this. Okay, so in this particular case 1 minus 0 is possible to be subtracted. Difference is 1, there is no borrow. Okay, 1 minus 1, difference is 0, there is no need to have the borrow. Now we cannot subtract 1 from 0. Okay, so it has to take borrow from the next candidate. It again doesn't have the magnitude. Okay, let me know the number again.
0,
0,
111,
111,
00,
yeah,
11. 0, 110, 110.
okay. So I have done this particular part and this particular part. Now here in this particular case, I just want to have the borrow from the previous one. Previous one also do not have the sufficient value to pass the borrow. Okay, so it will again ask for the borrow from the its previous. Okay, so it will give the borrow. It will get reduced. Now this will going to be 10. Okay, and this 10 is sufficient to borrow to the next one. Okay, यहाँ कितना आया 10, यहाँ कितना बचा 1 only. Okay, so in that particular case from 2 you are borrowing 1. Okay, so there is 1 left, and this contribution will increase the value in the radix, so it is going to be 10. From 10 if you subtract 1, it is going to be 1. Here we have only 1 left. 1 minus 1 is 0. Here at this particular place it is 0. 0 minus 0 is 0. Then 1 minus 1 is 0. 1 minus 1 is 0. 0 minus 0 is 0. So it is going to be marked with negative sign because we have interchanged the minute and subtrahend. Okay, depending upon its magnitude. So outcome is negative of 101. That was the answer that I have obtained. Is that clear now? All right. Multiplication. Multiplication is nothing but the AND operation. Okay. So AND outcome will be 1 only in case both the bits are 1. Otherwise it is going to be 0. Okay, so just look at the multiplication. 0 multiplied with 0 is going to be 0. 1 multiplied with 0 is 0. 0 multiplied with 1 is 0. 1 multiplied with 1 is only resulting in 1. Okay, so this multiplication result can be done for the multiple bits as well. So what you have to do, the same concept as you done in decimal. Okay, so pick one particular bit from the multiplier, apply the multiplication for each and every bit. Okay, then go for the next one, then go for the next one by skipping the place. Okay, every time. And once you have the partial product, apply the addition on that to get the overall result. Okay, so it is 1, 1 plus 0 is 1, 0, 0, 1 is 1, 1 plus 1 is going to be 0, and 1 borrow here. Okay, sorry, carry here. Okay, in that particular case 1, 0, 0 is going to be 1, and this is the 1. So it is going to be the final outcome of the product. Okay, just go for another example. Let's say I just want to have the multiplication of 25 with minus 5. multiply these two numbers in binary. So just consider only 5-bit representation. You are not supposed to go for the more than that. Okay, and one more important thing, like if bits are not specified, then it is better to just convert this. Let's say 25 is converted into binary as 16 plus 8, 24, 1. Okay, so it is going to be 11001. Okay, multiplied with 2's complement of 5, because that is going to be the negative number, so it has to be converted into 2's complement. So 5 is represented as 101, append 0 for the sign bit. Okay, and then find the 2's complement of it. The 1's complement is going to be 1010, add one more at the LSB to get the 2's complement, so it is going to be 1011. Okay, so minus 5 is going to be represented as 1011 in binary. Just apply the multiplication of this and get the result.
Last one extra bit.
Now that is possible.
100,
Okay, your multiplied outcome, na?
100,
100,
100,
100,
1.
11.
Last MSB is signified as a negative number.
हाँ, so overall product result will be negative, na? Yes. Just match with your result whether you are getting the same result or not. I am getting the same result. 100, 100, 11. Okay, those who are in live class, please let me know whether they are getting the same result or not. No response? Let me see who is there. Yeah, Farhan, are you there? Satish? Vaibhav? So, Sendra, please let me know whether you are getting the same result or not. All right, Satish and Manan Srivastava getting Srinivas getting the same result. What about others? Please participate, because see, this is not going to be the one way. Otherwise, there is no difference that you have spent in your 4 year. Okay, please participate and ask your doubt as much you can have. Okay. So we have very few more slides left. Let me complete this one. Okay. My screen is visible to you on Zoom. All right. So just look at the BCD arithmetic. That was binary addition, subtraction, and multiplication. Now look at the BCD arithmetic. So you have some number in BCD and you just want to have the addition on that. So just look at the example. 8 is represented as 1000 and 5 is represented as 0101. Okay, just apply the addition on this and your addition result is going to be 1101, which is equivalent to 13. Okay, and in BCD you cannot represent more than 0 to 9 because that is binary coded decimal. Okay, so your decimal can be only represented in that, so 0 to 9 can only be represented in such a case. Okay, if so, if your number is exceeding the desired range, in that particular case, to manage that particular number, what we can do, we can add 6 with the obtained result. Okay, so our result is going to be 1101. If I add 6 with this, you'll get the equivalent converted BCD. Just look at the option outcome. It is going to be 1, then 1, then it is 110. There will be a carry. 1 is going to be 0 and there will be a carry. Okay, now to convert it into equivalent BCD, append 3 zeros before this to have the equivalent BCD. Okay, now it is going to be 1 and this is going to be 3 in BCD. Okay, it is not 13, it is 1 3. Okay, so 3 is represented as 0010 and 1 is represented as 0001. Okay, so by visualization you can say both are same, but logically they are not same. Okay, because 13 is 1101, which is not able to be represented in BCD. Okay, to handle such scenario, what you have to do, you have to add 6 to convert that resultant into the equivalent BCD. Okay, 6 ही क्यों ऐड करते हैं, that is very good point. Okay, 9 plus 6 is going to be 15, which is the last range in 4-bit binary representation. So that will produce the carry for the next one. Okay. To you can say to transfer the information, that access information to the next bit, to the next BCD location, we are just trying to add 6. Okay. Solve it. This is BCD addition of these two numbers. So 1897 is added with 2905. Okay. So let me solve it first, and then you solve the remaining term. Okay. So I'm just adding the one term BCD. Just have your attention over here. Please have your attention over here. Then solve for the remaining 3 terms. First term is, let's say this 7 is added with 5. Okay. So in this particular case, you can see that 0 plus 1 plus 1, because by default carry is 0. LSB carry is always 0. So this is 0 plus 1 plus 1 is going to be 0 with 1 carry. Okay. 1 plus 1 is going to be 0 with 1 carry. 1 plus 1 plus 1 is going to be 1 with 1 carry, and this is going to be 1. Is it done? No. It is more than 9. Okay, it is more than 9. In that particular case, what we have to do? Add 6. 0, 1, 1, 0. If you add 6, what will be the outcome? It is going to be 0, then 1, 1, 1 is going to be 0, and then there will be a carry for this particular one. Okay, 1 plus 1 is going to be 0. Okay, and then there will be a carry. Now, where do we accommodate this carry? To the next term. Okay, so whatever carry is produced at this particular place is passed to the next term. Now you have to solve the remaining. Let me have the answer. Okay. So let me solve and see whether your answer is correct or not. Now again, it is going to be greater than this, so it has to be added with 6. 0, 0, 0, 0, and 1 is transferred over here. So it is 0, 1, 0, and 0, which is lesser than, or again we can have the carry which is greater than 6. Okay, so again we can add 0 1 0 1 1 1 0. Okay, then it is going to be 0 0 0 1 over here, and this one. So this one is supposed to be supplied to the next one. 1 1 is 0. This is carry is 0, then 1 and 0. So there is no need to apply any operation for this one because it is going to be lesser than 9. So outcome is going to be 0 1 0 0. Remove this, remove this. So your final outcome is in converted BCD, if I say it is 4 8 0 2 in BCD. Are you getting the same? सेकेंड लास्ट गलत हो गया बिकॉज आपने यहीं से कैरी आगे पहुंचा दिया. ठीक है, सो यू हैव टू केयर अबाउट दिस कि आप कैरी यहीं से डायरेक्ट पास नहीं कर सकते. जैसे ही आपने कैरी पास कर दिया, दिस नंबर इज ट्रीटेड एज लेसर देन 9, बट एक्चुअली इट इज नॉट. ओके, get the result, get the intermediate result, check whether that is lesser than 9. If it is not, apply addition of 6 with that. After having the result, pass the carry. Okay, is that clear to you all? Okay, so error detection code. So parity is the error detection code. In that particular case, what we do, we apply either even parity or odd parity. So what we can do, we can append one extra bit with the information to check whether the number of ones in that particular information is odd or even. Okay, so that is our choice whether for even parity the number of ones should be even, for odd parity number of ones should be odd. Okay, so what we can do, we can add one more information to make it odd parity or make it even parity. Okay, so just let me have information over here. Let's say this is the message. Okay, and I just want to convert it into even parity. So what information I need to append with this to make it even parity? Even parity says number of ones are going to be even, count of ones in the message should be even. Okay, so even starts with 0. That means if I append 0 over here, it will be even parity. Now if you look at this, number of ones in this particular message is 1, which is odd. To make it even, append 1. Okay, for this particular case also 0 1. Now this particular information is converted into even parity. For odd parity
1 0 0 1 0 1 1 0.
just count the number of ones. If they are already in the desired result, append 0. If it is not, append 1. Whether it is odd parity or even parity, just count the number of ones. If it is lesser than the desired one, okay, odd है, उससे कम मिल रहा है, that means even मिल रहा है, तो आप एक ऐड कर लो. Okay, that was so simple. So that is the even parity and odd parity. And whenever you get the result, what you have to do, you have to simply check whether it is following the same parity or not. Okay, if it is following the same parity, that means it is possible that your message is correct. Okay, if it is not, so any bit is flipped. If any bit is flipped, that means it is toggled from even parity to odd parity. If any bit is modified, it is toggled from even parity to odd parity. Okay, so that will cause you the error. Okay, if more than one bit is toggled, then it is possible that you are getting the wrong result with the correct parity. Okay, if more than one bit is toggled, in that particular case, it is possible that you are getting the wrong result with the same parity. ओके, सो पैरिटी चेक करने के लिए अपने को एक एल्गोरिथम चाहिए, दैट इज कॉल्ड हैमिंग कोड. ओके, तो वो आपको कंप्यूटर नेटवर्क में पढ़ाया जाएगा. सो आई एम नॉट गोइंग टू cover that topic over here. Okay, ASCII, here you can see that ASCII is represented in 7-bit binary. Okay, so in that particular case you can see that numbers are represented in 0 to 9, numbers are represented in 30H or 16 hexadecimal base or 239H. Okay, if you look at the table, you can see 0 to 9 are represented in ASCII code as 30H to 39H. Okay, similarly for small a to small z, it is represented as 61H to 7AH. Okay, or you can have the equivalent decimal. Okay, what will be the equivalent decimal for this? (97) to 122. Okay, just look at the ASCII table, you will get this particular information. Okay, similarly for capital A to capital Z, it is represented into 41H to 5AH. Okay, and if you look at this particular difference, it is nothing but 65. Okay, convert it into equivalent decimal, 65 to 90. Okay, so there is a clear difference between these two as 32. If you look at the decimal, it is going to be the difference of 32 in base 10. Okay, if you look at the hexadecimal, it is going to be 20H. Difference is going to be 20H. Okay, and if you convert this 20H into decimal, it is going to be 2 into 16 plus 0, that is 32. Okay, so how, say in C programming, what you have done, you to convert a particular lowercase into uppercase or uppercase into lowercase, what you have done, you have to add 32 or subtract 32, है ना? That you have done. What we can do other than this, apart from this? We can convert that particular number into binary. Okay, and just toggle the 6th bit. 32 is nothing but the 6th bit. Just flip that bit. 0 is converted into 1, case is converted. 1 is converted into 0, case is converted. No need to go for the complex operation of addition, subtraction and so. Just convert a particular number into binary and flip the 6th bit. So bitwise operation is very useful, very powerful. Whether you go for the GATE exam, master degree and so on, you must read bit manipulation in your any programming language. Okay, whatever comfortable language you have, just go for the bit manipulation in that particular language. Okay, so that is very important. All right, so Unicode, we have the extended ASCII. Unicode is having some extended ASCII. All emojis or other such kind of complex data can be represented with the Unicode. Okay, like ASCII can represent only 256 characters. It is represented by 7-bit binary, so it is only possible to have -128 to +128, and that is representing total 256 characters only. Okay, but in Unicode we can represent 65536 universal character codes, which is having a large bucket to represent. Okay, so all complex informations can be represented over here. Emojis and other similar terms can be represented in this. Okay, so this is another Unicode that is to represent the information. So I told you that codes are very useful for representing the informations. Okay, so I'll stop over here. Still you have the floating number system representation and its operation left from the number system. Okay, otherwise this particular concept is over. Okay, so in next class I'll start with the floating point representation and then few more questions related to the gate exam, and then we'll jump to the logic gates and all. Okay, thank you for the today's session. If you have any doubt, please write. So students, if you have any doubt, please write. Otherwise, I'll close this particular session. Do you want to have the feedback? Okay, so message is given to you. Please have this link, fill the feedback. All right. Thank you, Satish. So I'll close this session in 1 minute. And you have, so this session is extended, so you have only 15 minutes for the next class. Okay.